Hello all, welcome back to this course, Design of Fixed Wing UAV. I hope all of you are safe and sound. This is again Dr. Subramaniam Sadarla from the Department of Aerospace Engineering, IIT Kanpur. So this second part is in fact a continuation of what we have covered during the lecture series 1. So I don't consider this as a new course, and indeed it is not, right? So I don't want to again reintroduce the content that we are going to cover in this course. So, and in the first part, we have covered about the performance aspects, starting with some introductory concepts, and then we have covered the performance aspects and how performance aspects help us in weight estimation. And also, we started with some aspects of stability. To be frank, we started studying about longitudinal static stability, and then we reached up to a point where we can find out neutral point given a wing and tail combination. So that is where we ended the previous course. And yeah, I have got many requests from your friends saying that they were not able to do the first part of this course, and then they want to participate in this current course. So I would like to structure this course in such a way that these newcomers will also find it comfortable. So I will not repeat what the concepts that we have covered during the first lecture series. So I may not go into the detailed derivations of those, but I'll touch base all those. During the first week of this course, I'll try to cover a little bit about all the concepts that will be helpful even for those who already completed the first part and also for the newcomers, right? So we'll cover those concepts which will be useful in the current course, in the current lecture series. Yeah, so I'd like to say this course will cover an algorithm, right? So I would like to present a flow chart. So algorithm of design, the main emphasis is this course will try to address some of the subroutines or subroutines of the design process, right? So where we develop our own codes, since we all know design is an iterative process. So instead of depending upon pen and paper repeatedly, let us develop codes parallelly during the course, and then use them for solving some design problems, right? Design subroutines. So we are here to discuss about this. So basically, part 2, continuation from where we have left last time. So as I mentioned, in the first 1 week will be dedicated for revisiting those concepts which we'll be using in this course, and we'll again start with stability and briefly derive those expressions which we have arrived during the previous course, maybe during the last week of the previous course, right? We'll revisit that again and solve few example problems, and then proceed with our current design process. Okay. So let's consider the following flowchart that's going to talk about a typical design process, right? So we'll start with certain mission requirements, which are a set of statements that helps you, set of statements that you need to achieve, right, with that particular UAV. So you have mission requirements. So from these statements, we'll be able to at least figure out what will be the aim of this design, right? So in the sense, you will have certain geometric constraints from mission requirement statements as well as performance constraints. So for example, if you consider a high altitude HAL, right, high altitude and long endurance UAV. So that means you are looking at A higher endurance typically may not be a high speed UAV, right? So you will know certain range of these velocities at which you need to fly. You'll get to know. That means you definitely concentrate on a subsonic, lower subsonic UAV, right? So and then you know it flies at certain altitude, so you'll try to figure out which kind of propulsion system that I need to use, right? And also a medium, so you'll be asked, for example, if you are asked to carry a payload of so many kgs, then you'll typically know, once you know the kind of payload, you'll try to figure out what is the power requirement of the payload, right? And with that payload, for a UAV to lift that payload along with the other accessories, you'll start with certain geometric parameters, right? So again, mission requirements poses or corners your focus area, right? When you talk about HALE, you will be concentrating on UAVs which can perform flight at a lower subsonic speeds, right? So when you talk about a combat UAV, then you may be concentrating on higher subsonic or supersonic speeds. So along with them, basically constrains the kind of aerodynamic model that you have to consider during the design process. Apart from that, these mission requirements will also give you certain geometric constraints, right? May not be all definitely, but to some extent they will pose certain geometric constraints. So from these mission requirements, with a basic estimation of geometry, we can do a proper weight estimation, right? So from this mission requirements, you can perform weight estimation, right? So and then we can use this weight estimation and of course this mission requirements here will also be useful again, right? So we can use this for initial geometry or initial configuration selection. So again, this is an iterative approach, right? It has multiple steps in achieving this particular configuration, a particular configuration based upon mission requirement. So you start with geometric, right? So what you have will be constraints. So you'll try to iterate to achieve that, with those constraints you'll try to achieve certain, doing iterations you will be able to achieve certain geometry. Maybe you can say wing plan form, at least for the time being we can understand that way. At the same time, you'll also analyze, or say you'll in fact, this is guided by this performance aspects as well. So all these subroutines, so will work hand in hand, right, in order to figure out a particular configuration. Okay. So let's continue this here. So once you have this geometry, you can independently perform an empirical estimation. Right. So for this, what I require is a historical database as an input, right? So I have historical database. So this geometry selection will enable me to perform certain stability and performance analysis. So this particular right. So this analysis will help me to figure out the propulsion system or power plant selection. Right. So this performance, and from this performance analysis, once we are satisfied with it, then we'll go ahead for simulation. Right. The simulation we'll be talking about is as an aircraft flight simulation. Right. So for this flight simulation subroutine, what we need is a numerical model, right? So, or say what we have is the 6-Stoff equations of motion, right? So we have mathematical modeling, which will be used along with 6-Stoff, 6 degrees of freedom, equations of motion. We'll use a numerical integration. So these equations of motion in general result in a first order differential equations, right? Maybe linear or non-linear. So in order to solve them, we have to use some numerical algorithm. So we have to solve them simultaneously. So we'll use some numerical integration. So for this numerical integration to happen, we need to give initial flight conditions as an input, and also for this mathematical model you need to give aerodynamic parameters as an input. So for this 6-Stoff equations of motion, so the input you need to provide is regarding inertial and geometric parameters or details, you can say, right? So this will help us to figure out how the system behaves, or the current design that you are considering, how it behaves under various conditions, right? So if you're happy with this simulation results, then you can proceed to the next part. Which is a prototype fabrication. So in this prototype fabrication, again you have a structural design. So once you have the structural design, you may now go for a scaled down configuration, right? So that I'll include in the structural design itself. And then these are the major steps. I'm not going in detail at each and every level. So once you scale down the configuration, then you may go for fabrication methodology. Or in between, in the structural design, when I say, there is analysis as well. Once you have come up with the design, then you can use any of the existing analysis softwares, right? That will help you to figure out what are the structural stress as well as loads acting on this, right? And then fabrication, right? So this fabrication again includes the scale down, prototyping and manufacturing. Okay. So I require some more space here. What I can do, I'll try to reduce this one. This subroutine will talk about prototype development, right, or fabrication. So where you have structural analysis, design and analysis. And then scaling down the configuration. And then perform or carry out the manufacturing or fabrication process. So at each and every level, we have iterative approach. No? Apart from, say, at each and at each and every stage, we should also make a decision, right? If you're satisfied with this analysis, then you'll be going to this step, or you'll be either going to step A here, right, where I say this as step A, right? So once you have this, you'll go for this scale. Once you have the scale down model, you will go for wind tunnel testing. So you will do an experimental analysis, right? So the initial experimental, or once you have the design, once you are satisfied with the simulation results, and then you can go for the initial experimental analysis using wind tunnel testing. And then you can also perform scale down flight tests, right? You have the configuration. So before this, so you will do instrumentation as well. When you do the flight test, you will also do instrumentation here. Right? So instrumentation. So this can be like instrumented flight test as well as initial flight test without any instruments, right, to see the flying capabilities. Right. So instrumentation. So this entire design approach is from flight dynamic point of view. Okay. So and then flight test. So once you are happy with this data, go for the scaled up configuration, the full scale configuration, and again go for flight test data, where if you are not able to accommodate a full scale configuration in the wind tunnel, then you can directly go for the flight test, instrumented flight test, and perform experiments, right? Analyze the performance as well as estimate the parameters using existing parameter estimation techniques, right? And if you find any of this, if you need to change any of the parameters, say if you need to increase the damping, so you again revisit the stability analysis here. Either without changing the configuration, can we do it by changing the CG, right? So in a way you can shift the loads, rearrange the loads, and achieve the different CG location, and see the simulated response of it. And then you can proceed with the structural design, see if there is any change in the stresses that are acting at the joints, or the change in CG location, is it changing the load distribution significantly, right? So look at that and then proceed with the flight test, right? And then get the data. So the wind tunnel test is a costly affair again, and of course the flight test, right? So at each and every level you have an iterative approach here. So we may not be covering the entire part in this course, right? So the emphasis of this course is to get a inverse solution. See here, any of these design algorithms will talk about aerofoil selection in the first place, right? So I would like to approach this in an inverse way, where I'll take the mission requirements, right? So we'll have the mission requirements, and then we'll use those mission requirements along with performance and stability analysis, right? We'll get airfoil selection, geometry, and all the geometric parameters, say root chord, tip chord, and the reference area. So all these things as an output, including what should be the CL alpha of the entire aircraft, what should be the CL naught of the UAV, right? And also what should be the two-dimensional CL naught and CL alpha, right? We'll get that as an output, and we'll be concentrating only on lower subsonic speeds. So that particular algorithm will correspond to lower subsonic speeds. So what we'll be dealing with is, yeah, so coming back to this. In order to get that as an output, we need to give certain inputs, right, in terms of non-dimensional geometric parameters. Okay, so what we have is a weight estimation, and then, yeah, up to this it is similar. So weight estimation, in fact everything, so we'll have the same thing, flight conditions and constraints. So here in our previous discussion, like in our previous algorithm, so these empirical relations can be replaced by CFD simulations. So similarly, the aerodynamic parameters here, Instead of using them, we can use these CFD simulations as an input. Okay. So what we have, what we'll be doing is we'll consider the issues of stability and also performance. So we'll use this together, right? So for this stability criteria, in order to figure out this, we need, so we need some inputs in terms of aerodynamic design parameters. And we also require, so here we will also require some non-dimensional geometric parameters as an input. So the output from this particular subroutine will be geometry, airfoil data, and also engine capabilities. See, again, design is not will not be able to achieve straightforward, is a closed form solution for the design process, right? So, but here with this particular algorithm, we'll try to achieve, right, with, of course, with all these inputs in terms of aerodynamic design parameters as well as non-dimensional geometric parameters. We'll try to achieve these as a closed form solution from this algorithm. Okay. Right. So basically what you're going to have is, the details that you'll get is about the span, about the root chord and tip chord. So tail sizing, tail setting and location. So wing characteristics in terms of CL0, CL alpha, right? And the airfoil characteristics in terms of two-dimensional properties, CL0 and CL alpha. So this will be the aim of the current lecture series, right? So we'll develop various subroutines in order to achieve these particular parameters. So this particular analysis can be used as an initial or a preliminary design during the preliminary design analysis. When you add optimization techniques to this, that can be used for detailed design analysis, right? So, and again, I would like to clear certain misconceptions, general misconceptions about this course. So this course is not aimed at aero modeling. Right? We are not going to do any aero modeling stuff in this particular course. And moreover, we are not going to talk about the structural, and I am not an expert in that, definitely. Yeah, we are not going to talk about this structural design and analysis as well as aerodynamic design and optimization, right? And neither we are employing any of these optimization techniques here in order to come up with an optimal design. So this can be used, as I mentioned, this particular algorithm that we are going to develop can be used for preliminary design analysis, right? So, and once you have hands-on experience with this, then of course optimization techniques and all these are mathematical tricks which you can learn very easily, right? and apply those mathematical tricks or optimization techniques for this particular algorithm, so that you will get optimized values of these parameters. Fine. So we have 2 TAs in our course this time. So fortunately, Prabhajit is on campus. So meet Mr. Prabhajit. Yeah, you can take off your mask. So you can introduce yourself.
Hello all, myself Prabhajit Singh. So I am one of the TAs of this course, that is training assistant, and the other one is Qazi.
Yeah, that's our second TA is Qazi Salahuddin, who was TA for the first part of this course, and both the times when it was offered. So he was the TA, main TA for that course. So both of them will be helping us. And yes, we are talking about an iterative approach here. So we need to use any one of the programming language, and I would prefer MATLAB as I would prefer MATLAB here to program them. And I wish you should start learning MATLAB. So for those who are not comfortable with that, Prabhajit and Qazi will help you with some of the tutorials, right, in MATLAB. Okay.
Sure.
Sounds good?
Yeah.
Okay. Yeah. So in the coming lectures, we'll try to revisit some of the important concepts that we have already covered during our previous lecture series, and will be useful for the current design process that we are going to take up. Right? Okay then. See you soon.